Hi, my name is Gavin Scott, and today I'll be talking about design for investment casting with a focus on design for manufacturability. We'll look at how the casting process works, the design rules that help make parts easier and cheaper to produce, and how engineers can take advantage of this process for complex, high-precision components. Investment casting is a metal casting process that starts by creating a pattern, usually out of wax, that's coated with ceramic material to form a mold. Once the mold is built up, the wax is melted out, leaving a hollow space where molten metal can be poured in. That's actually where the term investment comes from. It means to completely cover something, which refers to coating the wax pattern in ceramic. This process is known for its high precision and ability to produce detailed parts, even with complex shapes. The wax pattern itself is usually made by injecting hot wax into a die that has been sized to account for both wax and metal shrinkage. For more complicated parts, multiple wax pieces might be joined together before moving on. In mass production, it's common to attach several patterns to a central wax sprue, forming what's called a pattern tree. This is dipped into a ceramic slurry, kind of like a really fine mix of silica and plaster, to build up the mold. The slurry layers are built up repeatedly to create a thick, durable shell. Once the shell dries, which usually takes about 8 hours, the wax is melted out in a process called dewaxing using heat or steam. Then the ceramic mold is preheated and molten metal is poured into it. While the gravity pouring is most common, some foundries use vacuum or centrifugal techniques for better control. After the metal cools and solidifies, the ceramic shell is broken away and the individual parts are cut from the tree and cleaned up. There's no parting line like in the other processes, but the connection to the sprue still needs to be ground off. This slide gives a quick rough comparison between investment casting and other metalworking methods in terms of part complexity and cost. While investment casting has a higher upfront cost, especially in tooling and processing steps, it becomes very cost effective for complex parts, especially when machining or welding would otherwise be required. Investment casting offers a lot of design freedom. You can cast parts with very intricate shapes, fine details, and tight tolerances, often within 75 thousandths of a millimeter or about 3 thousandths of an inch. You also get an excellent surface finish straight out of the mold. One big advantage is that the process produces near net shaped parts, which means little or no machining is needed afterward. That's a huge cost and time saver. The wax used for patterns can sometimes be reused, which also helps reduce waste. And although this is considered an expensive process overall, it can be very efficient, especially for small parts at complex geometries, including parts up to 75 pounds. It's also a great solution when switching from fabricated or welded assemblies. If you can cast a part in one piece instead of welding together multiple pieces, you save on labor, reduce lead time, and improve part strength and reliability. In terms of lead time, investment casting usually takes between 4 to 6 weeks, depending on the size and complexity of the part. Some common examples of investment casting are the production of pump and valve parts, components used in marine applications, military weapons, mining and forestry machinery, and turbine blades used in aerospace engines. The impeller shown here displays how much time and money using this process saves when compared to traditional machining processes. The swirler on the right is an example of a customer being able to reduce the number of components for an assembly by choosing a different manufacturing process. The two examples shown here also demonstrate how investment casting contributes to the concept of DFM, as certain applications can either save on machining or assembly time by utilizing a different process. Shown here are some of the tolerances that can be achieved utilizing investment casting. For part mass, the minimum will be about 1 gram, while the max part mass will be about 100 kilograms. For linear tolerances, 1 inch plus or minus 10 thousandths of an inch, and adding 5 thousandths of an inch for each additional inch. Flatness and straightness will be dependent on the foundry and its capabilities. Roundness will be about 15 thousandths of an inch on a 1 inch diameter radii. Surface finish will be RMS 63 to 125. Fillets will be a minimum of 10 thousandths of an inch, and castable wall thickness will be 40 thousandths of an inch to 2.96 inches. One of the biggest strengths of investment casting is its flexibility with materials. It works with a wide range of metals and alloys, especially those that have melting points below 2200 degrees Celsius. Let's start with carbon steel. It's popular because it offers a good balance of strength, flexibility, and affordability. You'll find carbon steel castings used in automotive gears, valves, and heavy machinery parts that need durability and precision. Stainless steel alloys are another common choice. These are great for parts that need corrosion resistance, like pump components, surgical tools, or food processing equipment. They're tougher to cast, but with the right process controls, you'll get excellent results. Brass and other non-ferrous metals like bronze and copper are often used when aesthetics matter. For example, in decorative pieces or components where heat transfer is more important than strength. Ultimately, the material you choose depends on your part's function, whether that's strength, corrosion resistance, biocompatibility, or thermal performance. The material will also influence things like how the mold is made and what kind of post-processing is needed. Listed here are some design constraints and considerations that should be taken into account when designing for investment casting. Streamlined shapes, rounded edges, and smooth transitions improve mold quality and reduce the likelihood of defects. Uneven wall thickness can lead to issues like warping or weak spots due to inconsistent cooling. Designing with uniform thickness enhances structural integrity and ensures a smoother casting process. In investment casting, natural wax shrinkage typically eliminates the need for draft angles, allowing for easier mold release. However, slight draft angles may be applied when shrinkage is insufficient or with ceramic cores to ensure smooth ejection. This flexibility enhances production efficiency while maintaining the process's precision and versatility. The challenge in designing for investment casting is to make full use of the enormous capability and flexibility inherent in the process to produce parts that are truly functional and cost-effective. Often such parts will also be more aesthetically pleasing. The principal advantages of investment casting that permit this challenge to be met are discussed here. Complexity. Almost any degree of external complexity, as well as a wide variety of internal complexity, can be achieved, and in certain cases, the only limitation is the state-of-the-art in ceramic core manufacturing. As a result, parts previously manufactured by assembling many individual components are currently being made as integral castings at a much lower cost and often with improved functionality. This ability to produce complexity with ease can even benefit simple parts, which can be redesigned to save weight without the loss of strength by providing I or H sections or thin walls with ribs. Thus, many parts from competitive processes can be converted to investment casting. Freedom of alloy selection is another quality. Any castable alloy can be used, including ones that are impossible to forge or are too difficult to machine. Further, the cost of the alloy is less important in the final price of an investment casting than it is in other metal forming processes. Therefore, an upgraded alloy can often be specified, especially if the part is redesigned to save weight, at little or no increase in price. Close dimensional tolerances. The absence of parting lines and the elimination of substantial amounts of machining by producing parts very close to final size and give investment casting an enormous advantage over sand casting and conventional forging. The availability of prototype and temporary tooling is a major advantage in the design and evaluation of parts. The direct machining of wax patterns or the use of any of the quick, inexpensive tooling methods described earlier facilitates timely collaboration between the designer and the foundry to produce parts that are functional and manufacturable. This capability is simply not found in such competitive processes as die casting, powder metallurgy, or forging. Further, temporary tooling used in the design phase can often serve for production while the market is tested or permanent tooling is constructed. Reliability. The long-standing use of investment castings in aircraft engines for the most demanding applications has fully demonstrated their ability to be manufactured to the highest standards. Wide range of applications. In addition to complex parts and parts that meet the most severe requirements, investment casting also produces many very simple parts competitively. This capability is often made possible by the low tooling costs associated with investment casting. Investment castings are competitively produced in sizes ranging from a few grams to more than 300 kilograms, and the upper limits continue to increase. The following recommendations provide a useful guide to the design of investment castings. Look for ways to implement the advantages mentioned previously. Focus on final component costs rather than casting costs. Design parts to eliminate unnecessary hot spots through changes in section sizes, use of uniform sections, location of intersections, and judicious use of fillets, radii, and ribs. Promote good communication between foundry and customer to resolve questions of functionality versus producibility. Use prototype castings to resolve questions of functionality, producibility, and cost. Do not overspecify. Permit broader than usual tolerances whenever possible. The design of the cluster, or the wax tree, is more important than it might seem. It affects almost every part of the investment casting process, from how efficiently parts are made to how well the metal flows into the mold. Some of the key factors include how easy the cluster is to assemble, how many parts can be processed at once, the strength of the assembly during handling, how the mold dries and how wax is removed, and how the metal flows and fills the mold. You also want to think about things like minimizing shrinkage defects, ensuring good grain structure, and making the ceramic shell easy to remove. On top of that, the cluster has to fit the foundry's equipment and processes. There are three big goals when designing a cluster. Make sure it's strong enough to survive the entire process. Ensure it meets all metallurgical requirements, and include separate test specimens if needed for things like chemical analysis. Getting the final part dimensions right starts all the way back at the pattern making stage. That means adding allowances for shrinkage, not just from the metal solidifying, but also from the wax cooling and shrinking. Traditionally, patterns are made using injection molding, where wax is injected into a metal die. The wax is usually injected at a temperature between 42 and 77 degrees Celsius and under relatively low pressure. Recently, new pattern making methods like 3D printing are being explored, which are great for prototypes or complex designs. As for materials, wax is still the most common. Researchers have found that blending different waxes or adding polymers can improve things like surface finish, flow, and dimensional stability. The ideal wax has low thermal expansion, good breakage resistance, a low melting point, and almost no ash when burned out. The better your pattern material, the better your final part quality, especially when casting tight tolerance or highly detailed components. For certain parts, especially those with complex internal geometries or high strength requirements, investment casting can be taken even further using special techniques, including core inserts and grain structure control. To create features like internal channels or cooling passages, foundries use ceramic or soluble cores. Soluble cores are made of water-soluble wax or polymers. They're inserted into the die and wax is injected around them. Afterward, the core is dissolved before the shell is built. Ceramic cores are more durable and can handle complex high-temperature applications. These are left in place during casting and removed afterward with a chemical bath or high-pressure process. Grain structure directly affects the strength and durability of the final part, especially in aerospace or turbine components. There are three main types of grain structure that can be achieved. Equiax grains is the default grain structure when the metal is simply poured and allowed to solidify naturally. Grains are roughly equal in all directions. It offers good general purpose strength and is the most common. The second type is directionally solidified. In this technique, Casting is cooled in a controlled way so that grains grow in a single direction, usually along the axis of highest stress. This removes transverse grain boundaries, improving fatigue and creep resistance in high temperature application. The third method is single crystal. This is the most advanced. Using very precise control, the casting is made to form just one continuous crystal structure with no grain boundaries at all. These are used in jet engine blades and other extremely demanding parts where grain boundaries would cause failure under heat and stress. Grain control techniques add time and cost, but they allow castings to perform in environments where conventional castings would not survive. Shown here are three of the same part with different grain structures. The first has an equiax grain structure, the second has a DS polycrystal grain structure, and the third has a DS single crystal structure. Thank you for watching this presentation, and these are the sources I use to gather information.